Hello everyone, and welcome to the 15th lecture of CS2100 Discrete Structures course. So we're switching topics now, and in today's lecture we'll cover introduction to combinatorics. So combinatorics is an area of computer science and statistics that deals with counting outcomes of various problems or experiments. So here is the outline of today's lecture that will be, as usual, split into two parts. So first we'll talk about what different outcomes for counting are and how to organize them. Then we'll introduce rules of products and sums, and also the rule of complements. After that, we'll talk about a bit more advanced rule called rule of sums with overlap. Then we'll show how we choose and count subsets. And finally, we'll cover the binomial theorem. So let's go ahead and start with the basics of counting. So for our first counting problem, we want to count how many ways can two winners be chosen from 4 competitors: Amy, Barbara, Chris, and Dinesh. Let's assume, to start with, that the same person cannot win both prizes and that the order of winners does not matter. So this is then equivalent to the problem of determining how many elements are in this set here. And so the elements of this set denote different configurations of winners if we assume that the same person cannot win both prizes and that the order of winners does not matter. So if you remember, the order of elements in a set does not matter. And so how many do we have? We can simply count 1, 2, 3, 4, 5, 6. So the answer to this problem is 6, and we can solve it by simply enumerating all the solutions. We'll see later on how we can actually compute this directly, which comes in handy if, for example, the number of competitors is much larger, let's say 50 competitors. When doing it manually by enumerating is not possible. Okay. Now, one thing to note here, and it was really important, is that it is really important to determine whether there is a first prize and a second prize. So meaning whether the order matters and whether the same person can win both. So in the previous slide, we saw the case where the same person cannot win both prizes, and the prizes are not different, meaning the order of how people win them does not matter. Here we enumerated 3 other possibilities. So the first one is that the order matters, meaning that there is a first prize that is distinct from the second prize, but the same person cannot win both. Then we have 2 distinct door prizes, so that means that the order matters and same person can win both. Then the 2 prizes are identical. That means that order does not matter and same person can win both. And so I enumerated these in this handy table in the bottom right that you can see here. So there is 4 different possibilities, and we can compute and count the outcomes for all 4. So as an exercise at home, you can try to enumerate the solutions for all of these. We already did it on the previous slide for this quadrant of this table. Maybe we can quickly do this one. So that's the situation where the order does not matter because the prizes are not different, but the same person can win both prizes. So that's the same solution as on the previous slide, except we are missing AA, BB, CC, and DD, because the same person can win both prizes. So that will be 6 plus 4, that's 10. And you can do the rest. Okay, a little bit about the terminology. So this is the same table from the previous slide. And each of these quadrants, depending on whether the repetitions are allowed and whether the order matters, has a well-established name. So if repetitions are allowed and the order matters, then we're talking about ordered lists. If repetitions are allowed and the order does not matter, then we are talking about unordered lists, which are also known as bags. If the repetitions are not allowed, but the order does matter, then we're talking about permutations. And if repetitions are not allowed and the order doesn't matter, we're talking about sets. So sets we've seen before, and in this lecture we'll see the other structures as well. So whenever you are faced with a counting problem, one of the first things you have to do is to determine in which of these 4 quadrants are you, depending on what the problem is asking for and how it's specified. And that's often actually even the hardest part of calculating the number of outcomes. So I want to talk a little bit about organization counting because it's really, really important and it comes up a lot. And students stumble on this quite a lot. Let's say we have to solve this simple problem where we have to enumerate all permutations of letters M-A-T-H. So what are the permutations? Permutation is a structure where the order does matter, but repetitions are not allowed. And so, we can kind of try to do it, and I kind of listed them haphazardly here. And now the question is, how the heck do we know that I actually accounted for all of them? I mean, if you just look at this, it looks like I ordered them I picked some random way to enumerate them, and it's really hard to know whether I managed to do all of them or not. And so, whenever you have to do something like this, you have to enumerate all possible permutations or something like that, it's good to have some kind of way of organizing your ordering. And here is one such way of doing that. That's not the strategy you have to pick. It's just one way of doing it. I think the general message here is that whenever you have to order or create the sequences of more than 2 or 3 elements, make sure that you have some kind of organization of how you're doing it. And here I organize by letters. Within each column, I organize the entries based on the second letter. So the first column, they all start with M, and then as you can see, the second letter I change between AA, TT, HH, and then in the second one, MM, TT, HH, and so on. And so now it's really easy for me to see that I did indeed enumerate all of them, and it's also really easy to count all of them. So I have 4 columns and 6 rows, and therefore 4 times 6, there's 24 entries here. So make sure when you have to enumerate all your solutions to have some kind of organization in place for when you're doing that, so that you don't either overcount or undercount their number. Okay. Okay, so let's continue this explicit enumeration story and try to enumerate all possible outcomes when we have two different door prizes. So recall in this case, the order matters and repeats are allowed. And again, you want some kind of organization, and what I did is that I imposed an alphabetical order. In the first row I have everybody starting with an A, then B, then C, then D, and the same across columns. So how many do we have? 16. Now, what if the door prizes are the same? So that means that we're in a situation where the order does not matter and repeats are allowed. What is the idea here? Well, we can simply modify the previous enumeration by excluding the ones where the winners are the same. So we have AB here. Here we had BA, but because order doesn't matter, these two are equivalent, and so we can erase one of them. So we are going to erase all of the ones in this bottom quadrant, and we can count this again. How many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the main message again here is that make sure to organize yourself when you are doing the counting, when you're enumerating all the possibilities. Okay, so in the previous slides we kind of showed how to solve these kinds of problems when it's easy to enumerate all possible outcomes. And that's perfectly fine way of solving these problems when the number of outcomes is relatively small. So when you have up to 20, 30 outcomes, okay, maybe you can enumerate them explicitly and just count them manually. However, it is more often than not the case that the number of outcomes is not small. In fact, it often goes into millions and hundreds of millions. In this case, we can clearly not list all of the outcomes and count them. And so we have different rules that we can use to directly compute the number of outcomes. And the first rule that we are going to talk about is called rule of products. So if each entry in a list can be created by selecting one of X objects and then selecting one of Y objects, then the list has a total of X times Y entries. For finite sets A and B, this means that the number of elements in their Cartesian product is equal to the number of elements in set A times the number of elements in set B. And here is an example. How many entries are made by selecting first from the set A, B, C, D, E, F, and second from the set 1, 2, 3, 4, 5. Well, you can maybe try to enumerate them, but that gets really time consuming really fast. Instead, we can use the rule of products. We have 6 elements in the first set, A, B, C, D, E, F, and 5 elements in the second set. And so the number of such entries will be 6 times 5, which is equal to 30. So that's one example of how rule of products works and how it can be applied. Okay, more on the rule of products. Here is another example. How many numbers between 100 and 1,000 have 3 distinct odd digits? So, what is the basic rule? We have 3 digits chosen from odd digits, so 1, 3, 5, 7, 9. And we cannot repeat them because they have to be distinct. So if we want to explicitly enumerate all of these, a nice way to organize it would be as this tree. So in the first step, we're picking any digit from these 5 digits. And then in the second step, we only have 4 digits available. Since they cannot be repeated, they have to be distinct. And so, if we're branching from 7, we're going to be able to branch only to 1, 3, 5, and 9. And then from here, we will only be able to branch into a set that has only 3 digits because we used up 2 of them and there is no repetition. So we can solve this problem indirectly by counting how many leaves are in this tree. And the rule of products, again, helps us here. So we have 5 choices in the first step, 4 choices in the second step, because we used up one of the digits, and 3 choices in the last step. And that's 5 times 3, 5 times 4 times 3, which is equal to 60. So there is 60 such numbers between 100 and 1,000 that have 3 distinct odd digits. And of course, I drew an example of this tree here to illustrate how the rule of products works here. When you're solving the problems, you don't have to draw this tree. You can just apply the rule of products directly. Okay, so similar to the rule of products, we also have the rule of sums. So it tells us that if a list can be split into 2 disjoint pieces of size x and y, then the original list has x plus y entries. For disjoint sets A and B, this means that the number of elements in their union is the number of elements in the first set plus the number of elements in the second set. Note that this holds only if they're disjoint. We'll introduce a rule later that deals with the situation when they're not disjoint. Here's an example. So how many positive integers less than 1,000 consist of distinct digits from this set 1, 3, 7, 9? So note that we have to think about all integers from 1 to 1,000. So we'll have 1-digit integers, 2-digit integers, and 3-digit integers. 1-digit integers is easy. We can simply enumerate them. So there are just 4 of them, 1, 3, 7, 9. 2-digit integers, we can compute using the rule of products that we introduced in the previous slide. So there is going to be 4 times 3, which is 12. 3-digit integers, there's going to be 4 times 3 times 2. So what is now the total number of integers from 1 to 1,000 that have distinct digits from positive integers that have distinct digits from the set drawn from the set 1, 3, 7, 9? Well, we have these 3 sets here: 1-digit, 2-digit, and 3-digit integers. They're not overlapping clearly, and so the total number is their sum. And when you sum this up, you get 40 integers. So this is the problem where we first apply the rule of products to compute the number of elements within each of these 3 options. And because they're not overlapping, then we can use the rule of sums to compute the total. Okay, so this is the rule of sums. So let's look at another example. So let's say we roll a die 3 times and record the results as an order list. And now the question is, how many ways are there to roll exactly 1, 1? Okay, so now we can divide this into 3 disjoint sets of triples with 1 in 3 different positions: first, second, and third. And here are the sets that illustrate this. So the first set has 1 in the first position, and then all possible ways that we can roll the other 2 positions. Then second set has 1 in the second position, and first and 3 positions have all possible ways of rolling die for these positions. And the same thing goes for the third set. So let's take the first set. So in the first set, there is one way to roll the first one. So that's clear. Then there are 5 ways to roll the next number, because we cannot have another one. And there are 5 ways to roll the last number, because they can repeat, but we cannot roll one. So there are 25 ways to roll the first set. And the other 2 sets are analogous to this first set. Okay? And note that they are not overlapping, so there is joint. So we can use rule of sums now. So we add 25 plus 25 plus 25, and we get 75 ways to roll 1, 1. So this is yet another example where we first apply the rule of product and then the rule of sum. And that's a very common pattern that you'll see a lot. Okay, the next rule is so-called the rule of complements. So it tells us if there are X objects and Y of those objects have a particular property, then the number of objects that do not have that property is X minus Y. So in terms of sets, for set A and the Rosa set U, this means that the number of elements in the complement of A is equal to the number of elements in the universe minus the number of elements in A. Again, we'll illustrate this as on an example. So how many rolls of 3 distinguishable dice result in the largest number showing being either a 5 or a 6? Okay, so first, what is the total number of possible rolls? Well, the first die can have 6 different rolls. The second die can have 6 different rolls, and the third die can have 6 different rolls. So there is 216 of total possible rolls. So that's our universe. That's the total number of possible outcomes. Then we can calculate the number of rolls without a 5 or a 6. So here we have 4 possible ways that we can roll the first die, because it cannot be 5 or 6. 4 for the second, and 4 for the third. So there is 64 different ways or different outcomes where we'll get the roll without 5 or 6. And then if we use the rule of complements, the number of rolls that have 5 or 6 is the total number minus the number of rolls that don't have 5 or 6, and so that's 152. So this is an indirect way to compute the number of rolls with a 5 or a 6. There are different ways that you can go about this. So you could try a direct way where you maybe calculate you have 5 on the first die, but not on the others. Then you have 5 on the first and second, and so on. But that will be a much lengthier procedure with many more calculations than this one. So rule of complements often allows us to get to the solution in a much more straightforward way than doing it directly. So that's where its power lies. So, if one thing is much easier to compute than its complement, then compute it and deduct it from the universe, and that way maybe you get to the result in a much faster way. Okay, so that's our rule of complements. So as promised, let's see how the rule of sums with overlap works, which covers the case that I mentioned before when the sets that we are counting are not disjoint. So if a list can be split into 2 pieces of sizes x and y, and those pieces have z objects in common, then the entire list has x plus y minus z entries. For finite sets A and B, this then means that n of A union B is equal to the number of elements in A plus the number of elements in B minus the number of elements in A intersection B. So this is the case when A and B are not disjoint. So here's an example. If we roll a die 3 times, how many outcomes have exactly 1, 1 or 1, 6? So as on the previous slide, first we count all outcomes with exactly 1, 1. And there is 75 different ways that such an outcome can appear. Then we count outcomes with exactly 1, 6. That there is again there is 75 ways that such an outcome can appear. And now, of course, there is an overlap of outcomes with exactly 1, 1 and 1, 6. Here we want to exclude those. So those are outcomes such as 1, 6, 2, 1, 2, 6, 2, 1, 6, and so on. And there will be 24 such outcomes. And now, if we apply the rule of sum with overlaps, we get that there is 75 plus 75 minus 24, which is the overlap, meaning there is 126 ways total to roll a die 3 times and get exactly 1, 1 or 1, 6. Okay, so next we will look into general formulas for counting different types of structures. And first we'll look at permutations. So the total number of ordered lists where repeats are allowed from elements drawn from the set of n elements of length r is n to the power of r. An example is how many binary sequences have length 5? And the answer is 2 to the power of 5, which is equal to 32, because we can only use 0 and 1 because they're binary sequences. So we are drawing from the set that has 2 elements, and the length is 5. The total number of permutations, which are sequences that don't have repetitions, like the previous ones, of length r on the set of n elements, is denoted as P of n comma r, and we compute it like this. So P of n comma r is equal to, we use the rule of sums, so any of the n elements can go to the first place, n minus 1 elements can go to the second place because we used 1, and so on, all the way to n minus r plus 1 because the length is r. And that is equal to n factorial divided by n minus r factorial. Just as a reminder, n factorial is equal to n times n minus 1 times n minus 2 times 2 times 1. So you multiply all numbers between 1 and n, and that's what n factorial means. So here is an example. How many 5-item grocery lists are possible for a shop that sells 20 products? So we are drawing permutations from a set of 20 elements, and the length is 5. So that's P of 20 comma 5, which is equal to 20 factorial divided by 15 factorial, which is this large number here. Note that when you're solving these problems in the quiz and in the homework, it is enough to just write down this expression. Often this is pretty hard to calculate, and so on the quiz we will not be looking for the final number if it's really large, and we will provide that as a note alongside the question. If the number is small, we will expect from you to calculate it. If it's really large, we'll give you a hint that you can leave it in this form. Okay. So as a special case, P and N is equal to N factorial. And an example that illustrates this is how many ways are there to arrange 4 people in a line. So we are drawing from the set of 4 people, and the length is also 4. So that's 4 factorial, which is equal to 24. Okay, so this is a general formula for permutations and ordered list. So let's now derive formulas for computing the other 2 structures that we have, and those are unordered lists and sets. So we'll do this by turning our attention to equivalence classes. In particular, we'll look at the problem of how many 2-element subsets there are in this set of 4 elements. And we can clearly see here that permutations are not the same as subsets, because in permutations the order matters. However, in subsets it does not. Moreover, an equivalence class is a set of objects that are considered equivalent to one another. Okay, so let's try to derive this formula for the number of subsets by starting with the expression that we have for permutations. So we know that there are P of 4, 2, which is equal to 12 permutations of 2 elements if we draw them from this set 1, 2, 3, 4. And now let's put these permutations into equivalence classes. So we consider 2 permutations equivalent if there are different representations of the same subset. So here are some examples of equivalence classes. So permutation 1, 3 and 3, 1 are equivalent because they contain the same elements. The only thing that's different is the order. The same goes for 4, 2, 2, 4, and so on. And now, since each equivalence class contains 2 permutations, there are 12 divided by 2, which is equal to 6 subsets of these 2-element subsets of this set of elements 1, 2, 3, 4. Okay, so this was an example. So let's see how we would derive a general formula for this, starting with permutations. So this concept is called choosing subsets. So C of n, r is the number of subsets of the set of n elements of size r. We also read this as n choose r, or r combinations from this set. And then C of n, r is equal to P n, r divided by r factorials, which is equal to, when you work this out a little bit, n factorial divided by r factorial times n minus r factorial. We can sketch a simple proof for this. So consider a single subset of a length r. And now there are P of r, r, which is equal to r factorials, distinct permutations of this set that are counted as a part of P and R. So this many distinct permutations belong to the same equivalence class. And so because every subset is counted r factorial times when we are using permutations, we have to divide the total number of these permutations, P n, r, with r factorial to get the number of combinations. So that's how we derive this final expression. Okay, to summarize all of this, here are ways of counting different structures. So ordered lists of length r, so those are the ones that allow repetitions. The number of possibilities is n to the power of r. Permutations of length r, it's P n, r. Unordered lists of size r, the number is C of r plus n minus 1, r. and sets of size R, the number is C of n comma R. And then in addition to these basic ways of counting, on top of them, we apply our rules of products, sums, complements, and sums with overlap as needed. And that's how we will be solving problems in this area. Okay, here's an example. In how many ways can we arrange six children in a circle? Okay, so let's consider the 6 slots they must walk into. And therefore, there is P 6, 6, which is equal to 6 factorial, which is equal to 620 different arrangements. Now, let's consider all arrangements in which every child has the same left neighbor and the same right neighbor. So imagine a circle that rotates. Or you can think of equivalence classes. So how many ways are there to get the same arrangement is this new definition? And then how many distinct arrangements are there by this new definition? Given that there are 6 slots in this circle, each equivalence class is going to have 6 different arrangements of children. So you can imagine rotating children in a circle once you have an arrangement. And then how many distinct arrangements are there? There is 620 divided by 6, which is 120 arrangements. So that's the solution for this problem. Let's look at another example. So it's asking how many ways are there to draw a flush in a 5-card poker game. And if you've never played poker, doesn't matter. You just have to know that flush is 5 cards of the same suite, or the same suit. And a standard deck has 52 cards, 4 suits, and therefore 13 cards in each suit. So we're going to apply a 2-step algorithm for solving. So first we are going to choose a suit of this flush. And there are 4 different ways to do that. Then we're going to choose 5 cards from this suit because any 5 cards, and the order doesn't matter, constitutes a flush. So we're going to choose 5 out of 13, and that's 1287 ways. And now by rule of products, we have to multiply this, and there are 5,148 ways to draw a flush. Okay, let's do one more example that uses combinations. So we have a club of 10 seniors and 8 freshmen, and they are trying to form a committee of 5 people. In how many different ways this committee is possible? We're choosing 5 people from 18, so it's that amounts to 8,568. The key thing to note here is that the order doesn't matter, and we choose any 5 people. Now, how many committees contain exactly 3 seniors? Well, first, we are going to choose these 3 seniors. There is 120 ways of doing that. And then we have to fill in the rest of spaces with freshmen. There is 28 ways of doing that. And then we apply rule of product, and we get 3,360 ways. Finally, how many committees there are that contain at least 3 seniors. So one way of doing this is to solve how many committees there are with 3 seniors and 2 freshmen, 4 seniors, 1 freshman, and 5 seniors, 0 freshmen. And then we add them up because we're using the rule of product here, and they're disjoint clearly. And so here's the expression that calculates